Assalamu alaikum everyone. Myself Muhammad Fahim Hossain Sarkar and my ID is 2401016. And my teammates are
Assalamu alaikum. I am in the Shahin Alam and my ID is 2401025.
Assalamu alaikum. Myself Forhad Ahamed Nirob. My ID is 2401015.
Assalamu alaikum. My name is Jillur Rahman and my ID is 2401005.
today we will demonstrate our data structure and algorithm stational force project smart work and disaster shelter management system. Our honorable course teacher is Ahamed, Assistant Professor, Department of Internet of Things and Robotics Engineering, University of Frontier Technology, Bangladesh. Our project introduction and problem description. Frequent floods demand automated, reliable management system to ensure survival. Lack of real-time occupancy tracking leads to chaotic shelter allocation. Manual records and unoptimized routes slow down critical life-saving operations. What is the problem statement of our project? Our problem statement is inefficient resource allocation and delayed rescue response due to the absence of advanced data-driven coordination tools during flood crisis. Manual management of shelters, victims, and emergency requests leads to delays. Poor coordination and ineffective use of available resources. A centralized and optimized system is required to improve disaster response efficiency. What is the objective of our project? Our objective is shelter safety, fast registration, rescue priority, route finding, optimal aid, auto reports. Here is our system architecture. First, we start our program, then user security to verify validation and access, shelter initialization, then victim registration. Here we can register victims. Victim allocation, here we can allocate shelter to a victim. Emergency alert, priority rescue, route finder, then resource optimization, then shouting reports, then central storage. And here is the end of our pipeline. For the next part, I'm willing to invite my teammate and the Shahin Alam.
So thank you to my friend Fahim. Now I will discuss about the BSA concept that we use in our system, our project. So in for shelter management, we use AVL3 for fast search and balance update. For victim records, we use also AVL3 for higher efficient global loop. For shelter occupants, we use linked list. So we can easily add victims to our shelters. For emergency QE, we use DQE. So the critical patients are added to the front and the normal patients are added to the rear. For rescue priority, we use Maxi. So prioritize severity based life saving responses. For route optimization, we use graph plus Dijkstra algorithm. It uses the real-time shortest path to incident sites. Now, I will discuss about the AVL3 and the things. We use AVL3 in shelter management system and victim management system. The main advantage of AVL3 that it balances the trees. It ensures that search time remains zero of log n even for large datasets by maintaining tree balance. In linked list, we use it used within each shelter node to store victims dynamically. It allows one condition, one addition of new survivors. Next, I will discuss about the QEs and priority management in our project. So mainly QE follows FIFO rules. FIFO means fast in, fast out. We use DQ in emergency request. If there are any critical requests, we add it to front, and if there are any standard or normal requests, we add it to rear. It allows flexible handling or varying severities. Now I discuss about the maxi that we use in priority rescue. So we set the priorities of critical patient is 100. We set the priority of injured is 80. We set for elderly, we set it 70. For child, it's 60. The route always holds the highest risk victim. Example, if we add a critical patient. So the critical patient will be the root. Next, I will discuss about the optimization and pathfinding. So for optimization or pathfinding, we mainly use the Dijkstra algorithm. So in graphs, the nodes are the food zones, hospitals or shelters, and the edges are the distance or time. The goal is the fastest rescue route. So we use the dynamic programming in our project. Mainly, we use 0, 1 knapsack for rescue aid. It optimizes food, water, and medicine based on several values and capacity. Now I will discuss about the detailed process and designs. So the execution starts from the login page. After success login, we can register a new patient or new victims and emergency trial. So shorted also at the same time shorted route calculation is triggered simultaneously with rescue optimization and ensure aid arrives with the rescue. So this is the logical flow of our project. It starts from the login page, then register, then process emergency, then assign priority of victims, then route finder and a dynamic programming. Then it reports to user and our system then ends the program. So now I will invite my teammate Forhad Ahamed to continue the presentation.
Shahin, I will explain time and space complexity of our algorithm used in our system. This algorithm average case, worst case, and space complexity. AVLT average case big O log n, worst case big O log n, space complexity big O n. Linked list average case big O n search, worst case big O 1 insert, and space complexity big O n. Max heap average case big O 1 root pick, post case big O log n delete, space complexity big O n. Dijkstra average case big O v plus e log v, worst case big O e log v, space complexity big O v plus e. Marshot average case big O n log n, worst case big O n log n, space complexity big O n. Knapsack average case big O nw, worst case big O NW, space complexity big O NW. AVL use shelter search, linked list use victim information, massive use highest priority request, Dijkstra algorithm use safest route, next step use resource efficiency. The next slide shows recurrent relation analysis. AVL balanced recurrent relation here and Marshot. Next step, dynamic programming efficiency gained by memorizing overlapping subproblems. Recursive relation here performance without dynamic programming big O n to the power n without dynamic programming table big O nw. The user interface system UI and input output. On the left side logging page, user enter their username and password to start the system, and on the right side is dashboard. Here's shelter management, victim management, emergency request, rescue priority, route finder, resource optimizer, reports, undo operation, and lockout. Now, my teammates Zillo present the next slide.
Thank you, Nirob. Now I will continue our presentation. Here is a screenshot of our shelter management system. And the next page, here is a screenshot of our victim management system. This slide shows the evolution of our system and future plans. First, let me talk about the advantage. Our system provides high-speed searching using AVL which makes data retrieval very fast. It also gives accurate priority sorting, so important tasks are handled fast. We have efficient path optimization, which helps to reduce time and resources. Now, moving to the limitations. Currently, the system is limited to a desktop-based swing application. Some records still require manual dependency, which reduce automation. It does not support real-time GPS synchronization, so live tracking is not available. Finally, for future work, we aim to develop Android and iOS application for mobile users. We plan to add cloud database for better storage and access. In future, we want to include AI-based productive modeling for smarter decisions. We also plan to connect an IoT sensor to enable real-time data collection. Now, my teammate MD Fahim Sarkar will demonstrate the project prototype.
Thank you, Jillur, for giving me the floor. Now I will show our DSA project. So this is the our DSA project code. So now I will demonstrate the project. It takes little bit time. Yeah, here we go. So now we give the admin username, then the password, our login. Here you see the login is successful. So this is our dashboard. Uh, this is shelter management system. So here you can give the shelter information like shelter ID, shelter name, location, capacity. So here you can see we give a shelter information KT001, name is Kaliakoi, location is Gazipur, capacity 50, occupancy is 0. So here you can add shelter, search shelter, update shelter, delete shelter, or we can refresh shelter. Now we see the victim management system. So here victim registration need, victim ID, name, age, medical condition, priority level, assign shelter. The priority level there have critical, injured, elderly, child, normal. Assign shelter, here we can see all of the shelter name we register. So here we can also register victim, search, delete, and refresh. So as long that they also have emergency request, rescue priority, route finder, rescue optimizer, reports, undo operation, and logout. So if we go to the report section, we can see the total report section. Victim by priority. Here we have the victims. Here we have the age of victims, shelter occupancy, and statistics. If we go to the emergency request, we can see new emergency request, soft alert critical, medical request, food request, process, next request. Then if we go to the route finder, then here we give some dummy location. We don't have actual location currently, so there have some dummy location. So if we give some dummy location like shelter 3 to shelter 1 and give the find shortest path, we see the statistics. And then we have rescue priority. If we check this, we have ID, name, priority, medical condition. Or we can process next rescue, view, rescue, queue, add selected victim to rescue queue. So here it is. That's all for today. Thank you.
Now, conclusion. The system successfully integrates advanced DSA concept to provide a live critical solution for disaster management. By replacing manual triage with APL3 and disaster pathfinding, reaction time are significantly reduced, potentially saving thousands of lives during flood crisis. Thank you.